This is the screencast for section 7.2, example 7, saving time with geometry formulas. Okay, so yeah, you have a choice between integrating between dy and dx, and sometimes it seems really obvious, but there's a little trick that we could follow. In example 7 here, we're going to see how maybe a little shortcut will help cut down the work significantly. So we're going to find the area of the region in example 4 by subtracting the area of the triangular region from the area under the square root curve. Okay, so first of all, let's just pretend it just said find the area and not giving us any hints on how to do this. Well, I'm looking for the area of this shape, which is odd. If I wanted to do a dx problem, my top and bottoms are square root x and y equals 0 up until the value 2. Then I'd have to change them because the top is still square root x, but the bottom is now x minus 2. Alright, or I could do a dy problem, and then my left and right, or right and left of side of the rectangles does stay the same throughout. So it kind of looks like a dy problem would be good. But now there's a third option. What if we do a dx problem, but we integrate all the way through from 0 to 4? So that means I'm actually going to find the area of all of this. And then what I can do is subtract out this perfect triangle, and the area of a triangle is just a simple geometry formula. So that will make this problem a little bit easier than splitting the upper and lower boundaries for dx or changing it into a dy problem. Alright, so let's do that. Let's find the total area and take the area under the square root minus the little triangle. Well, the area under the square root curve is then going to integrate from 0 to 4, so all the way through the big block of the square root of x. Then we're going to subtract out the area of the triangle, which is 1/2 base times height, or 1/2 2 times 2. So now I'll integrate and evaluate from 0 to 4, but then minus, and this is just a simple multiplication, 2. Fundamental theorem part 2, and I get 10/3 units squared, or 3 1/3 square units, which makes sense because of if this is a 4 by 2 rectangle, this looks like a little less than half of that, and we did this problem before too. So we found the whole area from 0 to 4 and then took out the piece of the triangle to find just what was left over. So let's try that strategy on the now try problem number 35. On number 35, find the area of the region by subtracting the area of the triangular region from the area of the larger region. Well, again, let's pretend they didn't tell us that. The region on or above the x-axis bounded by the curves y squared equals x plus 3 and y equals 2x. So on or above the x-axis, and then I solved for y to be able to graph that, and then I've got 2x there. So basically, I'm looking to find this area right here. And yes, I can make a dx problem out of this with 2 pieces, or I can make a dy problem out of it, but I also have the option, because what's missing here is just a nice triangle. So I could find the area for that triangle and subtract it out after I integrate all the way through this piece in a dx situation. So first I'll start integrating from -3 all the way out until 1, and that's going to be the area under the curve square root x plus 3, so the total area under the curve. Then I'm going to subtract out the piece of triangle here, which has base 1 and height 2, and then so I take 1/2 base times height. So I find the antiderivative, fundamental theorem part 2, and of course that triangle simplifies down to an area of 1, and I get 4 1/3 square units of area.